Yay, we're at the last topic in Chapter 1 of the Math 2 book. And the last section is the cube root function. The cube root function is f of x equals the cube root of x. So if we make a table of values and plug in, for instance, -8, we get -2 for f of x. Now, -2 to the third power, -2 times -2 times -2 is -8. So the cube root function says what to the third power equals -8? Well, that's -2. And then we can see the other values in the table. So plotting those points on a graph, this is what our cube root function looks like. So now we want to identify some of the key features of the cube root function. Our first set of key features is the domain and range. The domain is the x values, and we can see that the x values continue on for infinity to the left, so to -infinity. They continue on to positive infinity to the right. We can include 0. We can include integers, fractions, everything. So the domain is all real numbers. The range is the y values, and we can see that the y values will continue to get lower and lower and lower to -infinity. And as we go for x values that are positive, the y values continue to go to positive infinity. So the range is all real numbers. We also want to identify the intercepts. The x-intercept is where the graph crosses the x-axis. Well, that's at the origin, 0, 0, which is also where the graph crosses the y-axis. So the y-intercept is 0, 0. Our other key feature that we want to identify is this graph increasing or decreasing? We read a graph from left to right. So as we read from left to right, the y values are continuing to increase throughout the entire graph. And so is this increasing or decreasing throughout the entire graph? This is an increasing function. One of the things we might want to do is look at maximum and minimum values within an interval. Maximum and minimum values are the y values in that interval. So what are the maximum and minimum values for f of x equals cube root of x over the interval x is between -8 and +8? So we want to look at that interval. Our lowest value is -8, our highest value is +8. So we're looking at the interval between those two values. So we see at -8, the graph has the point -8, -2. At +8, the graph has the point 8, 2. So on the left interval, the lowest y value of the graph is -2. On the right interval, the highest y value of the graph is +2. So the maximum value is 2 and the minimum value is -2 within that interval. All right, now you try this one. What are the maximum and minimum values for f of x equals cube root of x over the interval x is between -27 and +27? Pause the presentation, figure out your answer, and then resume. The cube root of -27 is -3. The cube root of +27 is +3. And so the maximum value is 3 and the minimum value is -3 within that interval. Now, the next thing we want to do is translate the cube root function. Move it left or right or up or down. So we want to compare the two functions, f of x equals cube root of x and f of x equals cube root of x plus 4. What do you think will happen to the graph when we add plus 4 at the end of the function? Well, let's go to Desmos and figure this out. We're going to put in the function f of x equals, and now we want cube root. When we bring up our keyboard, we see square root, but we don't see cube root. So we go to functions, and over in miscellaneous functions, we have the nth root. And so we're going to pick the nth root, and it's cursor is up where to put the index. So we're going to put in 3 and then x. So there's the cube root of x. And then we'll add the function f of x equals, and then again we want cube root. So we're going to grab the nth root and put the cube root of x. And then we add plus 4 at the end. So now by adding plus 4, this graph moved up 4 units. Here it went from 0 to 4. Here it goes from 2 to 6. So that graph moved up 4 units. So we look at the graph that moved up 4 units by adding plus 4 at the end. Now let's compare. So we had f of x equals cube root of x plus k. That plus k moves the graph up or down. So that is a vertical translation. Now let's compare f of x equals cube root of x and f of x equals cube root of x minus 6. So we have our original function, f of x equals cube root of x, and now we're going to put minus 6 inside the cube root function. So now we can see that this graph moved to the right 6 units. So by putting in the x minus 6 in the parentheses, it moved the graph to the right 6 units. So adding something inside the function, f of x equals cube root of x minus h, moves that graph left to right, so that is a horizontal translation. Remember, our convention here is x minus 8, h. So x minus 6 moved it to the right 6 units. All right, how is the graph f of x equals cube root of x minus 2 translated from the parent function f of x equals cube root of x? If you said it's moved down 2, that's correct. Putting something on the end is a vertical translation. How is the graph f of x equals cube root of x plus 5 translated from the parent graph f of x equals cube root of x? If you said that that graph moves left 5, then you're correct. Remember, we have x minus, so x minus negative 5 would look like x plus 5. So that moved to the left 5 units. Now we want to look at a problem using a cube root function and model that information. So we have some clay packages, and each clay cube contains 8 cubic inches of clay. So we want to modify the volume. We want to increase the volume within that cube. So when we increase the volume, we don't know what the new volume is. We'll call it x. So the new volume is x cubic inches. So our question is, for what increase in volume would the side length increase between 1 inch and 2 inches? When we increase the volume, how's that going to affect the length of the side? Well, our volume, we said, is going to be x, so the length of the side of a cube would be the cube root of x, because the volume is the side cubed. So our new package has a volume of x, our old package has a volume of 8, and so the difference in those two volumes is going to be x minus 8. And so the change in the length of the side of the cube is going to be the cube root of x minus 8. So now we go to Desmos again, and let's look at the cube root of x minus 8. So we have the cube, we had the cube root of x minus 6, so we have the cube root of x minus 8. So here's our function. And within this function, we want to look at the interval between 1 and 2 inches. So we're going to blow this graph up a little bit, and we're looking at between 1 and 2 inches. This is the volume that we want to change. So the side length, which is the y value, is changed between 1 and 2 inches. So if we take that section of the graph where we had the between 1 and 2 inches, and we kind of distorted the graph by pushing it in a little bit. Okay, we're looking between the 1 and the 2 inches. We're looking in this section. The lowest value at the 1 is 9. So if I put in the 9 for x, 9 minus 8 is 1. The cube root of 1 is 1. The highest point where we get to the 2 is 16, 2. 16 minus 8 is 8. Cube root of 8 is 2. So between those y values, 1 and 2, we have volumes that are going from 9 to 16. So increasing the volume between 9 and 16 cubic inches would increase the side length between 1 and 2 inches. All right, here's a question for you to answer. If a cube has a volume of 10 cubic centimeters, and a larger cube has a volume of x cubic centimeters, what would the value f of 14 represent for the function f of x equals cube root of x minus 10? So we're not asking for a value, we're asking what does that f of 14 represent? F of 14 would be the difference in the side length between a cube with a volume of 14 cubic centimeters and a cube with a volume of 10 cubic centimeters. Next, we want to compare rates of change in a single function. So in the function f of x equals cube root of x minus 1, we want to know how does the rate of change from x equals 1 to x equals 5 compare to the rate of change from x equals 5 to x equals 9. So we're looking at two intervals, from 1 to 5 and from 5 to 9. So what we want to do then is find the values at 1, 5, and 9, the values of the function at that point. So f of 1 would be cube root of 1 minus 1, which is 0. F of 5 would be cube root of 5 minus 1, which is approximately 1.59. And f of 9 would be the cube root of 9 minus 1, or 2. So looking at the interval from 1 to 5, we'd have the change in y over the change in x. The change in the y values, f of 5 minus f of 1, over the change in x, 5 minus 1. Well, we said 5 was 1.59 and f of 1 is 0. So 1.59 minus 0 over 4 is approximately equal to 0.4. From 5 to 9, we'd have f of 9 minus f of 5, so we have those two values, and then the 5 minus, or the 9 minus 5 on the bottom, and so the change in that interval is approximately 0.1. So now, which value is bigger? Since 0.4 is bigger, when we look at the graph above 1, okay, we might have something else going on before 1, but as we look at the graph above 1, as x increases, the average rate of change decreases. Okay, this was a larger rate of change. So 1 to 5 was larger, 5 to 9 further along is smaller. So the average rate of change is decreasing. All right, here's something for you to do. Read the problem, figure out the answer, pause the presentation, and then see if you got the right answer. Compare the average rate of change for f of x equals 2 times the cube root of x minus 3 over the intervals x between negative 12 and negative 8 and x between negative 4 and 0. Figure that out and then come back. Looking at the boundaries, f of negative 12, f of negative 8, and f of negative 4, and finally f of 0, we get these values. So now, comparing the rates of change between negative 12 and negative 8, we use these values, the change in y over the change in x, and we get 0.121. For the interval negative 4 to 0, we're looking at these values, and so we compare the change in y over the change in x, and we get 0.2355. And since 0.2355 is greater than 0.121, there is a greater rate of change in the interval of negative or x between negative 4 and 0. So now, that was comparing rate of change in a single function. Let's look at comparing rates of change between two different functions. So we're going to be given two functions that are translations of f of x equals cube root of x. The first is a graph, g of x. The second is a table, h of x. So given those two functions, we want to say what has a greater rate of change in the interval x between 2 and 4. Well, on the graph, we can see that that cube root function got slid to the left 2. So g is a translation of f to the left 2 units. So g of x is the function cube root of x plus 2. So that's what we can use to find values in this interval. H of x is a table, so we can just use the values from the table. So for g of 4, plugging in a 4, and then g of 2, plugging in a 2, we get the two values 1.82 and 1.59. So again, our rate of change is the change in y over the change in x. So that gives us a value approximately equal to 0.115. For h, we can just use the values in the table. We have 2 is 2.48 and 4 is 2.81. So using those values, we can find the rate of change for h is approximately 0.165. So which one has a greater rate of change? Since 0.165 is greater than 0.115, h of x has a greater rate of change than g of x in the interval x between 2 and 4. So now, here's a problem for you to try. Which function has the greater rate of change over the interval x between negative 5 and 0? Either the function that's a translation of f of x equals cube root of x to the right 1 unit and up 2 units, or the function r of x equals cube root of x plus 3. Pause the presentation, figure that out, and then come back and see if you got the right answer. F of x got translated to the right 1 and up 2. So f of x is cube root of x minus 1 plus 2. And we were given r, cube root of x plus 3. So looking at the values for negative 5 and 0, and then finding the change in y over the change in x, we get 0.1634. For r, looking at the values for r of negative 5 and r of 0, and then finding the change in y over the change in x, we get 0.342. Since 0.342 is greater than 0.1634, r of x has a greater rate of change than f of x over the given interval. So, in review, when we look at the function f of x equals cube root of x minus h plus k, looking at how h and k affect the graph, we're going to put in h plus k, and then we see when we change h, that moves that graph left or right. When we change k, that moves the graph up or down. So when h is a negative number, so we'd get x minus a negative number becomes x plus something, that moves the graph to the left. When we get x minus, then h is a positive number, moves it to the right. K, a positive number, moves the graph up, a negative number moves the graph down. So for the function f of x equals cube root of x minus 8 plus 2, how is that graph translated from the parent function? I hope you said right 8 and up 2. Then you'd be correct. The function f of x equals cube root of x plus 3 plus 6. How is that translated from the parent function? Yes, it's moved left 3 and up 6. F of x equals cube root of x minus 5 minus 9. How is that translated from the parent function? That's moved right 5 and down 9. And finally, f of x equals cube root of x plus 4 minus 7. How is that translated from the parent function? It's moved left 4 and down 7. So, this completes Chapter 1 in the Math 2 book.